Hello everyone and welcome to today's webinar. Today's webinar is going to be conducted by Mr. Jitendra Manwani. Jitendra Manwani is a geotechnical engineering professional with more than 16 years of experience in the field of civil and tunnel engineering. For last more than a decade, he has been involved in multiple TBM and NATM tunneling projects in India and abroad. Mr. Manwani has received his MTech degree in geotechnical engineering from IIT Roorkee in year 2008. Currently, he is working as a senior geotechnical engineer, looking after civil design and underground packages of DC-05 Metro Line of Delhi, contact package R6UG RT01, Reach 6 Line Bangalore Metro Rail Project, Chennai Metro Rail Project, and others in Tamil Nadu and Manipur. His professional interests include tunneling works, instrumentation and monitoring, ground improvement and risk management, deep excavation, geosynthesis, project coordination, and geotechnical investigation and design. Some notable underground projects he was involved with earlier in various capacities are metro projects of Bangalore, Mumbai, Pune, Delhi Railway Tunnel in Manipur, highway tunnels, etc. Hydropower projects in J&K as well. Once again, I give a thank you for being part of the TAIym, sir, and I will hand over the platform to you.
Thank you, Aditya. I think I can continue from now on.
Yes, yes, sir, please.
Yeah. For a long brief about my works, thank you so much. I will continue with my presentation now. I wanted to firstly thank TAIym for giving us the platform to to present our work in front of all the audience. And this is webinar 48, year 2024. And I myself, Jitendra Manwani, my introduction is already given by Aditya. Basically, I'm a senior geotechnical engineer, project manager for NATM Works in Geoconsult India Private Limited. Geoconsult India Private Limited, basically, it's a private consultancy organization. We are basically comes from the Salzburg, Austria, and we are more than 400 employees. In India, we have base office in Gurugram, Haryana, and we are specializing in civil engineering field, geotechnical engineering field, consultancy services. Some specialization include NATM tunneling, slope stabilization, geology, underground design, consultancy services, etc. These are all our expertise. Then let me take you to my presentation contents. These are the presentation contents I will be presenting today to all of the attendees. Historical development of NATM. I will try to cover it with the images so that not to becoming boring. NATM design principles. This is important aspect. Geotechnical design of NATM. Determination of the ground behavior type for the NATM design. What are the challenges we normally face during the NATM works in India? Majorly in India, and I've worked in abroad projects also. So some of the challenges are common outside as well, but majorly in India, what I've seen, I will be presenting. Some INM related challenges are there. Some execution related challenges are there. So I'll try to cover it brief in front of you. Majorly in part of my presentation, I'll be focusing on one of the metro project case study where I'll be presenting a design aspect of a station excavation, which is a combination of cut and cover and the NATM tunnel. And I will be focusing on the modeling part, instrumentation part for the ground instruments.
Sir, I guess your screen is not moving, sir.
Yeah, I'll just move it. Then I'll be presenting later on the building damage assessment part. Now is it moving? Is it moving now?
No.
Still,
Just
no,
there is
sir.
a slide.
I'll do it again. I'll share it again.
And press the presentation.
Yeah, I'll share.
Sir, I will request you to present in a presentation mode. Sir.
Yeah, it is now. Now you can see that my screen is moving. Still not moving.
Moving, but
Still not
you
moving.
jump. You
Stuck
jump
on a single
for.
slide.
I'll go
You
to the
jump-
previous slide now. Now you can see the contents of my presentation now.
You jump
We are
to
still on the slide of historical development of NITM, sir.
Yeah, so I'll be jumping to the next slide now. What you can see,
Still the same slide, sir.
and now images are changing.
So I will request you to just reshare the presentation if
Yeah,
that will work.
I'll try to reshare it. Now you can, I hope you can see the presentation slide.
Yes, yes.
Okay, is it fine? So I'll be start with
Yes.
the first slide, the historical development. Firstly, the English method. English method is aimed at the quick closure of the final lining as the temporary support at that time served as a timber with the beams, as you can see in the horizontal direction. I'll just take the pointer. And if possible, those were moved forward with the excavation only when the final lining is installed. So after the final lining installed, next step is to do the next excavation method. So this is a typical image for the German method, where you can see the side walls are constructed first, and then after completion of the side walls, you can see the top heading is covered. Belgian method is more modern comparative to the previous method, which is having a sequential excavation with the top heading and benching, which is applicable for a wide variety of the ground condition. Of course, because it is in the sequential manner, so it will be rather slow in progress. This is a glimpse of Austrian method, where you can see the plan view and the front view and the side view of the first glimpse of Austrian method. The first idea of NITM, Rebswitz in 1948 patented a tunneling method which was based on double concrete shell approach, where the inner lining should be installed when the deformations are seized. Quickly installed primary lining should be avoid disintegration and thus development of the dead load on the liner. So with this method, the waterproofing between the primary and the inner lining was made possible. And the design of lining, inner lining, can be done based on the measuring results. So this is the sketch which was firstly presented in the lecture Geomechanics Dialogue in 1962 in Salzburg by Mr. Rebswitz, where he gave the method name New Austrian Tunneling Method, where you can see the original design is shown on the left side, which was later on modified to optimize design. This is a type of image where the NITM works has been shown. You can see clearly in the image, the top heading is already excavated and the bench excavation is in progress, and invert excavation yet to be done. You can see clearly systematic bolts all around the benching and the top heading, where you can see somewhere the lining stress controller, meaning this particular condition is squeezing ground condition with a high overburden. To absorb the deformation, normally lining stress controllers are provided. So what are the basic principles of the NITM? Firstly, you have to prevent the disintegration of the rock mass so that we can keep its original strength. How we use the rock mass as far as possible to additional stresses which is resulting because of the excavation. This implies that deformation should not be completely stopped right after the excavation, but it has to be kept below the critical levels so that loosening doesn't happen. Monitoring is of the behavior of the system to observe the stabilization process and allow the adjustment of the construction measures as per the ground condition. That is the important part for the NITM works. I'll be briefing about the geotechnical design of the NITM tunnels with the cyclic or conventional excavation. This is a flow chart where you can see which was presented in the Austrian Society Geomechanic Guideline for underground structures in year 2010. The first thing is to do the determination of the ground type. That is the most important thing you have to do. How you do the ground type determination? You first develop the geological model. How you do the geological model? You do the confirmatory borehole, and then you do the laboratory investigation out of the sample extracted from that particular details, and with the help of geophysical investigation, which can be surplus in addition to these borehole investigation data in form of ERT or ERI, you can cross-check your data from whatever comes from the borehole. So this is the example of the results, what you get it from the laboratory investigation. You get the mechanical properties of the samples at various locations. You get the UCS, you get the shear properties, tensile strength, modulus properties, and then you record the discontinuity data. Not only from the surface, you can record it from the borehole as well. So there are methods to extract the data. This includes the discontinuity, spacing, condition of the discontinuity, joint condition, etc. GSI, which is important. And then based on these inputs, you can derive the rock mass strength parameters, including the UCS of the rock mass, shear strength of the rock mass, and the deformation modulus of the rock mass, which is important for the designing part. After you complete the ground type determination, the next step is to do the ground behavior determination for the NATM works. So there are several influencing factors which governs the behavior type, which ranges from the ground type. What are the ground type? What are the stress conditions? What is the size of the opening you have? What is the size of the opening, and what is the position, whether it is deeper or shallower? What are the discontinuity pattern, whether it's a single highly fractured jointed rock mass, or there is a close spacing of the joint or higher spacing of the joint. This is very important to do, understand the kinematic analysis and the stress distribution in the surrounding. Boundaries between the different layers. Suppose you have soil condition and then rock, you have different profiles. So those boundaries are important to understand. And other than that, if you have the points related, some details related to the groundwater or the seepage force, etc., these are important to understand the behavior. So as per the Austrian guidelines, 11 categories of behavior, ground behavior has been classified. I'll be briefly talking about individual ground behavior. Stable ground, you can imagine a rock mass which is a highly massive rock mass. There are very few joints. You can classify this first category accordingly. Whereas in the point two, it will be potential of discontinuity control block failure. So this is a kind of example where you have the rock mass where some amount of joint sets are present. The spacing is they are far spaced, not closely spaced. You can equate here. Majorly voluminous discontinuity control failure will be there, or gravity induced failing and sliding will be there. Shallow failure normally happen in both the cases, with the discontinuity failure and gravity induced failure. This point number 3 is the example of normally in the urban tunneling what we have seen. Voluminous stress induced failure, the fourth category. It is normally you see when there is a large deformation. So I would say where you have the highly fractured or jointed rock mass with the high overburden, there is a large chances of high volume loss or large deformation. So sort of you can equate this with the mountain tunneling, something where the high overburden is there. Rock busting is basically the sudden and violent failure of the rock mass caused by the highly stressed brittle rock mass where rapid release of energy takes place. Buckling is again the joint play a role here for the buckling ground behavior, where you have the narrowly spaced discontinuities set which are associated with the shear failure. Crown failure, again, we have seen this sort of failure in the urban tunneling where voluminous overbreak of the crown and progressive shear happens with the condition where strata is very weak, grade 4 or grade 5 sort of rock, or soil condition in the urban ground where the normally covers are in order of 15 to 20 meter depth, 10 to 20 meter depth around. Reveling ground condition and flowing ground condition, I will give you example where intensely fractured, poorly interlocked rock or soil condition with a low friction. Only the difference in the reveling, it will be dry or moist, whereas in the flowing, it will be completely flow of water. That is a major difference. Swelling ground condition is the time-dependent volume increase of the ground caused by the physical chemical reaction. And then the last is the combination of these different types of ground behavior. So I'll be showing some of the example where you can see the discontinuity control overback. You can see on the right image. This is one of the example of the discontinuity control failure. Second image, if you can see on my screen, is you can see a large deformation taken place here. And because of the large deformation, most of the support has been damaged. So this is kind of failure where you have the high amount of stresses present. So one of the picture I'm showing where the collapse has been happened, daylighting has been happened with sometime it is damages to the third parties and sometime it is in the open ground. So this is one of the example where spalling has taken place in the brittle failure with the strong rock mass. This is normally seen in strong rock masses. So buckling, as I explained in the previous slide, where the joint plays a role, thinly foliated joint, buckling normally takes place. And for the brittle rock mass with the high accumulation of the energy, rock bursting takes place. So this is these are the examples of these sort of failures. In flow, one of the behavior type I explained in the previous slide, where you see the water is coming on the left side, but there is no the flow of the material, whereas in the right side, water comes along with the flow of the material, which is very dangerous situation. Then after doing the ground type understanding and then behavior type understanding, next step is to understand the system behavior or the defining the support classes for a particular tunneling system. So I'll be giving you a brief about some of the typical support measures. This is a stable ground condition, one of the example where you can see the full face excavation you can normally permit, where the ground is much better and limited amount of lining shotcrete thickness is there. And only spot bolts are given because to control the local wedges only. So it is only on the stable ground where the blocks are massive. This is one of the example where the wedges are formed due to more than two joint sets, and it is making a wedge, and you are stitching the blocks with the help of rock bolts. You give the enough fixed length of the bolts so as to protect against this falling block. So there are tools available in the software to check the design of these particular cases. This is one of the example of the shallow failure where you can see comparative to stable ground, the spacing of the rock bolts. These are systematic spacing where you can see the bolts are provided all along the overt and the invert portion, and the excavation may happen in the stages or the full phase, depend upon the condition. And the lining thickness will be slightly higher than the stable ground condition. Normally, we can say 150 or something can be there. Depend on the condition. This is a typical example. So this is one of the example where you have the in the high stress zone and you are completely in the fracture rock mass or the soil condition. You can see now excavation has been divided into three zones. Top heading has been done separately, then bench excavation, and then invert excavation. One of the image I earlier presented. So something where you have the weaker condition, you have definitely four poles on the crown part, and then you have the temporary invert, and then you have the elephant foot to cater the stress, the high stress transfer to the ground surface, and then you have the comparatively longer bolts and closely spaced bolt. And again, with the weaker ground, the face stability is very important, and the relieving of the pore pressure is very important. So you have seen a long numbers of drainage holes and the face stability bolts. So, and the comparatively thickness of the spread concrete is also higher, more than 300 mm round, with the two-layer wire mesh and the lattice girder. This is one of the example where the rock bursting taken place. So the rock mass is stitched with the net at fixed anchor points, so that avoiding any harm to the manpower on the masonry. This is example where the foliation joints are striking into the NATM, and the buckling zone has been created, and this has been stitched with the help of bolts. Now, this is an example of the weaker ground condition where we go with the pipe roofing at every 12 meter, 10 to 12 meter round, where you can see a present case excavation is happen in stages where top heading is supported with the pipe roof. 9.6 meter length of the pipe roof at 3 rounds of pipe roofs are there, and there is a 5.4 meter overlap after every round. So to bring it total 15 meter of length of pipe roof. So typical image of the revealing ground condition I explained in the previous slide, where there is the moist or dry condition is there present in the, and very weak strata where is almost no cohesion or shear strength is there. So this is type of support you normally recommend. This is the standard example where you have the flowing ground condition, and you can see the excavation now, how close the excavation has been happening here. You have the 6 set of excavation stages to complete your overt, and then you 3 stages to complete your invert. And again, these have been completely supported with your pipe roof. And then drainage layers are present all around, to 15-meter long, to cater to release the pore pressure. So this is very important to plan the stages of excavation, especially in the flowing ground condition. We have seen ample number of Indian projects where the progress is very little and slow. So it has to be planned in proper manner in terms of sequencing and the supporting arrangement. Rock bolts are not provided probably because of the soil condition. So one of the example of the swelling ground condition, where you can see the lining thickness, the spread concrete thickness is in order of 300 to 400 mm, and the SN bolts are provided fully grouted 12-meter in the invert portion. So typical flow chart, how we do the design. Once we have the geotechnical relevant parameter and we determine the ground types, we have some boundary conditions such as groundwater stress condition, what is the orientation of the tunnel, size and the shape and the location of the structure. We can able to determine the behavior, ground behavior, with the help of the design models. So this has been presented in terms of a flow chart. So some challenges I will be talking about related to the instrumentation. So as you know that instrumentation is a major pillar of the NATM. Sometime what has been seen on site, that intermittent interpretation and evaluation of the monitoring data happens, which is normally weakening the major pillar of the NATM. I will be presenting my case with an example. You can see uh, a plan of the tunnel has been presented, and the L section of the tunnel has been presented, and on the below slide you can see the graph of the vertical displacement. So once tunnel is entering close to the fault zone, you see sudden increase of the vertical displacement taking place, and then once it is entered into the fault zone, it again bring back to normal. Crown displacement, the blue color, is also getting impacted because it is hit on the right wall. So right wall is majorly hit, but crown is also hitting. Once it is entered fully into the fault, then it is back to the normal. So these are the important aspect which you can understand how important is the instrumentation for the tunneling. Sometimes what we have seen, that targets are damaged. This is very common thing what we have seen, especially near the face where there is no protection given, and due to the blasting most of the targets damaged. So that has to be considered in the NATM designing. Sometimes monitoring is taken as treated as a hindrance rather than necessity. So that is a very important thing that has to be considered. In the cycle time analysis, instrumentation is monitoring is not considered in separately. This is one of the thing which we have to be taken care. Survey team sometime asked to do the monitoring rather than engaging a separate team for dedicated monitoring. I'm not saying that every project, some of the projects what we have witnessed, we have seen these things, and they are asked to do the monitoring along with the surveying, so which is should be avoided. Some of the execution related challenges I wanted to highlight, that sometimes as per the designer recommendation that support has to be installed right after the phase, but sometimes more than 2 or 3 rounds are exposed without any support, so which is making critical for any tunnel. For the weaker ground condition, we give the elephant foot for the transfer of the stress. Sometimes doing the benching, that elephant foot is chopped away, so which is not good for the tunneling. It is critical. It is making critical things. Sometimes sealing layer, which is important aspect. When you do the tunneling, you immediately apply sealing layer, but sometimes it has been uh, not been carried out at site. Old shortcut machines are used which are unable to apply more than 50 thick lining, so that has to be avoided. Some of the challenges, execution related challenges are there. For example, one of the challenges, when water is getting accumulated on the surface of the tunnel, it is making the road damage, and it is making vehicle breakdown, more vehicle breakdown, which will cost more fuel, more downtime. So that has to be taken care. The channelizing of water is an important aspect. For the sometimes steel ribs and backfill concrete used instead of the shotcrete and the lattice girder. One of these common thing we have seen, the backfilling concrete for the vehicular movement has been constructed with the conventional concrete, which is making a bond with the invert, and when you take out the backfill concrete, it breaks along with the lining, the invert lining, so which is making things difficult. Some educational institutes are there now. It is things are improving, but still very few institutes offering tunneling related courses. Now there's improvement seen in this particular regard. For many government clients, you can decision making is absent, which is crucial for the tunneling. So now one of the case study I will be trying to present, where I will be covering the excavation of a station, the sequencing of the station and the modeling and the instrumentation aspect. So this is one of the example of the urban tunneling project, where you can see a cut and cover station has been shown on the left side, and the on the bottom side TAIym tunnel has been shown, and this complete station has been connected with the help of various cross passages, which is coming from the cut and cover side. Anyone can ask why you cannot make a complete cut and cover rather than doing a combination. So there is the thing that we need normally 24-25 meter width to construct the station, complete cut and cover station. Because of the challenges, urban tunneling challenges, we were unable to get this required width, and hence we were bound to do the part of the cut and cover and part of the TAIym to complete the challenges related to the urban tunneling. So again, as per my previous explanation, first thing you develop the geological model, and then you develop the geotechnical parameter. After developing these aspect, you develop the basic construction sequence, and then you do the analysis, whether it is analytical, empirical, or numerical. Then you evaluate the results from the sequence and the models. And if the calculations are correct, you go for the support study and the detailed sequence. If suppose your calculations have some flaws, you can revisit your calculation and recheck the different support system, or you can do the different challenges what you can see, and reapply the support system and redo the design. And of course, after doing this, you have to execute the drawings, but again it's an observational approach. So whatever you do, you give onto the site, it has to be monitored, and accordingly, if any amendments are there required at site, you have to do. So the plan I've shown previously, the section will look like this. I will be briefing. This is a cut and cover station. You can see the depth of the station is around 23 to 24 meter below the ground, and this is the tunnel which you can see from the earlier plan. It's constructed right close to the cut and cover box, and this is being connected with the help of the cross passages at various interval. This is the isometric view of this TAIym tunnel section and the cross passage. So firstly, first stage is to complete the cut and cover works up to certain level, and then the TBM will be passed through the station, where after application of the sacrificial segment. And once the cut and cover is reached to the bottom, you fill to the bottom of the top heading of the cross passage, which this is the cross passage, and then you can go ahead with the construction of the cross passage. So I'll be explaining on the next slide. So you can see once we complete the fill part, we can start excavating the cross passage. This is standard sequence where the section of the cross passage will look like this. Only this part we have started constructing. So we apply the pre-support before the entry into the cut and cover. Then we apply the drainage hole where required. If the seepage is high, you apply more number of drainage holes. Then you entered with the help of the 4-pole, and you apply the rock bolting and supporting. You do it in the 3 stages. I explained it 1T, 2T, and 3T in the 3 stages till the corner of the TAIym tunnel. The section will look like this. Of course, after each round of excavation, you have to apply the sealing layer. Then after completion of the sealing layer, you install the lattice girder and the remaining thickness of the shotcrete. I'll be explaining in the support system in the subsequent slides. Then once you touch close to the TAIym tunnel, you you start changing your section slightly to the vertical, and it is very important that you go with the sequence, because we are entering into the NATM, so additional support measure in the form of GFRP bolts are recommended, and this excavation has been done with the proper rock bolting system, and then which is on the side walls and also onto the crown. And once you complete the excavation, you have to immediately apply sealing layer after each stage of excavation, and you apply the remaining layer of the spread concrete lining. This way you can enter into the NATM tunnel. So next step, once you entered into the NATM tunnel, so this is the plan. You can see we have now entered into the NATM tunnel with the different section. Now the section is wider. It is the intersection zone. You divide your excavation into two stages. We call this portion as top heading 1. The width may be around 3 meter, and then this length will be around 4 to 5 meter. So this portion looks like in the section, and this portion looks like in the L section. And these the parts of the construction will be, I called it 60, 70, 80, 90, and 10T. So this height will be varying for different sections. As you can see, this is I'm showing the maximum section. So it will be reduced in the subsequent stages. So again, you have to install the spread concrete lining. You install the lattice girder and remaining shortcut after each round of excavation. After completion of this part, you can take on the other top heading 2 part in the same manner and apply the support system accordingly. So once you complete your junction part, now you have the face available for the NATM tunnel works. So this portion, which is shown on the plan, this you can take on this first and this second portion. We called it 16 and 19T with the top heading excavation. So whatever is the sacrificial segment, you remove the sacrificial segment, you do the remaining excavation of the NATM tunnel, you apply the support, and you can go on with the top heading excavation. So after completion of the top heading in the cross passage and the NATM tunnel, next step, you do the excavation of the invert portion. So in the cross passage, you can see the invert excavation has been done in the stages 2I, 1I, 2I, and 3I. So 1I, once you complete the 1I, you start filling the backfill up to the certain level, so that you have the vehicular movement, because you need the vehicle to move around to take out the muck or something. So you need something to backfill. So in the same way, you can do it for the 4I, but you have to remove the segment in the stages, the sacrificial segment. So after doing the cross passage invert, you can carry on the excavation of the NATM platform tunnel invert in the same manner in the sequential excavation. So after the planning of the sequence, now I will be briefing about the type of geology we got it for this particular problem. So we have basically the filled up material for the top 3-meter layer, and then next 3 to 4.5 meter layer is the silty sand. In the cut and cover design, which is for the cut and cover construction, which was done with the help of D walls, the ground level was taken slightly higher side. So total depth of the soil was conservatively taken 8.3 meter. And then we derived the rock parameter, which was given in the basic geotechnical parameters, as I explained in the previous slide. You can see it was happened in the poor quartzitic rock, where the rock class is grade 4, and you can see the deformation modulus is in order of 600 to 1200 MPa, and there is a good amount of friction and cohesion. So it is kind of good rock mass you can consider, but not very good, but comparatively blocky rock mass. So this is one of the example how we use the modified generalized Hook and Brown method using the Rock Lab tool, by using the inputs from the for the GSI and the UCS from the laboratory investigation, and to derive our rock mass parameter. This is one of the example of the grade 4 rock. So after doing the previous aspect, next thing is to do the convergence confinement. Convergence loss is very important aspect. You need to know where to apply support system. So whatever relaxation has been taken place. So we use the convergence confinement method by Mark Pennett to derive the convergence assigned to our design models. So for doing this, we calculated what is the sectional area of our tunnel excluding the TBM. So we calculated the equivalent radius correspondingly, and for the pull length which we have assigned for our design, we calculated the relaxation at different lengths. And these relaxation we simulated conservatively for our RS2 analysis. You can see the station and the TBM has been done in the earlier stages, and then we for the rock pillar which is connecting the cut and cover station, I'll be just briefing the section. So rock pillar is basically this is the rock pillar which has been simulated with the help of the RS2 modeling. I'll be explaining the next slide. And then you you apply the relaxation at the excavation phase, and then sequentially apply the relaxation for the top heading portion, and then subsequently after the completion of the top heading, you apply the relaxation in the same manner for the benching and invert portion. So this is the summary of the relaxation we considered at the face as well as at the point of the support installation. So how we did the modeling? So basically, I wanted to highlight this is the NATM tunnel we would like to design. There is a pillar which is connecting the cut and cover station with the NATM. So basically, what we try to did, because of the construction of the TBM and then cut and cover, that the stress field before the construction of this cross passage will change due to the prior excavation activities. Hence, the cross passage is modeled. So this particular cross passage is separately modeled in the modified stress field, which has been achieved by increasing the unit weight. So you can see this layer, we increase the unit weight. So how we did this actually, I try and explain in the stages. We created this model one firstly, where we model the NATM tunnel and along with the TBM and the cut and cover, and then at this pillar, we find out the variation in the stresses. So whatever variation of stresses are there, proportionately we increase the unit weight. Suppose this particular layer, the increase of the stress is 3 times. So unit weight proportionally increases. This particular layer, it is 1.5 times. So accordingly, unit weight is increased 1.5 times. This is we done to simulate the ground behavior at the pillar location. So after constructing the model, one thing it is important to see, relaxation for the cross passage has been considered 100% conservatively to check the stresses due to the CP excavation. This is a very conservative assumption. Normally, you have some relaxation, not 100%, but it is conservatively considered. So once we created this model to simulate this condition of pillar condition in a separate model, we find out the stress difference before the construction of the cross passage and after construction of the cross passage at this crown level. So whatever is the difference, we found out from the model 3 that whatever difference was there, we actually simulated on the crown of the cross passage. So this difference we found out was 335 kilonewton per meter square. So now this is the way we simulated the impact of this cross passage in our basic model. We called it model 3 in order to conclude our design. So these are the steps for completion of our modeling. You can see the 1 to 6 the stages are there where the cut and cover station is taking place till the concourse level. Then TBM will be passed through. Then excavation below the cut and cover D wall level with the rock with the proper supporting arrangement between stages 9 to 23 till we reach to the 23 meter below the ground level taken place with the proper support arrangement of cut and cover. Then here you make the impact of your the cross passage pillar with the help of surcharge, which you simulated from model 1 and 2. And after completion of this, you now start an enlargement of your top heading in the sequential manner. So you apply the relaxation at the excavation phase, at the point of support installation, and intermediate stage when your shotcrete achieve a required strength, 70% strength, and then you complete spread concrete 100% strength, which is far away distance from the face of the tunnel. And in the same way, you apply the relaxation and the application of spread concrete for the bench and invert portion as well. So after doing this, this is the summary of the results which we found out. You can see the deformation is in order of 13 mm in the crown portion, and the side wall it was in the order of 9 mm. This is the ground condition was much better. Therefore, you can see this range of deformation and settlement with so much of construction activity is in the order of 17 mm. And the forces, what we found out, is in order of 1327 and 34 bending moment. These forces we extracted and then we checked it, we factored it to check it in our internal design spreadsheet, which is developed based on IS 456, where we use the reinforcement which we use in the form of lattice girder and the wire mesh, and we check the support capacity with the different forces points within the limits. So this is how we justify the adequacy of our support system. And now once we have the design ready, we recommend the lining thickness of 200 mm and a sequential bolt length 6 meter, 5 to 6 meter in range. Close to the curtain cover, the length is slightly reduced because of the interference. However, for the other zones, it is 6 meter. 4 poles have been provided at alternate round in the platform tunnel, and the 200 mm thick lining with the 2-layer wire mesh with the lattice girder has been recommended. And accordingly, support has been given. Important thing, the drainage pipes are provided to release the water pressure, and the weep holes along the every round has been provided so that water dissipate and not create any issues during the construction. Similar support system was recommended for the cross passage, which is connecting the curtain cover to the NATM tunnel. You can see the section is slightly narrow in the width, but height is more or less same. So, however, the support we kept it same with the same length of the bolts and almost same spacing of the bolt, as well as the 4-pole and all other things. We kept it same. Cross passage is slightly critical, so rather than alternate round, we kept the 4-pole on each round because the length is normally 6 to 8 meter. So after doing the primary support design, the most important part, as I addressed in my previous slide, is the monitoring aspect. You can see at every cross passage location we come up with the section A, which is basically more number of instruments. Whereas in section B, we try and give only optical targets every 5-meter interval. Whereas in the junction, we on the each side, somewhere in the middle, we try and give the more number of instrument. I'll be showing you the section which we used it. Section A, you can see detailed instruments are there, which consist of load cell for the bolts, strain gauge to monitor the strains, and then radial pressure cell to get the pressure on the on the shortgate lining, and then 3D targets to monitor the horizontal and vertical deformations on the crowns and the sidewalls, and as well as on the invert. So how we do the AAA limits? Basically, whatever we got from the RS2 modeling, we convert this force into the stresses, and with the help of hoop stress theory for the thin cylinder, we get the radial stress. So you can see there is a formula P into R into T, where N is the stress which is coming onto the liner, and with the help of the thickness of the lining and the radius of the tunnel, we get the radial stress, and we divide our AAA limits to 0.5 times serviceability, 0.8 times serviceability, and 100 times serviceability. And for the strain gauge, we using the modulus of the lining, the factored modulus. Normally it is 29 GPa, so it is factored to some amount, 0.8 times. And then we found out using the relation E is equal to force divided by area. We stress upon strain. We find out the micro strain, and then again we given the AAA limits accordingly. For this particular project, because of the multiple round of excavation, we kept the vertical settlement in order of 25 mm, horizontal settlement for inclinometer and all other monitoring aspects 15 mm maximum side. So however, we give the monitoring in these stages. I will be explaining in the others the next slides. So after the doing the primary support and then instrumentation for the NATM, the next step is the buildings, right, which is coming onto the alignment. So in order to carry out the building impact assessment, building as adjacent to the alignment is classified in terms of the proposed risk of the damage. What is the risk of the damage based? So we divide the categories of the damage which is given by Mr. Burland et al. 1977, Boscardin and Cording 1989, showed that these categories of damage are related to the magnitude of maximum tensile stress. So the classification you can see depends on the maximum tensile strain limits. So if the limits are in order of 0.05, it is negligible. The limits are in order of 0.05 to 0.075, it is in slight. Whereas if the limit is greater than 0.3, it is categorized into severe and very severe category. You can equate these things with the help of the damage to the buildings, where the cracks are hairline only, or fine cracks are there, or buildings needed extensive repair or major repairs. So you can classify with the help of this. So for doing this, there are 3 steps of assessment. The first step is to you develop the influence zone surrounding the stations. And so I'll give you a brief influence zone. Normally we consider 30 to 50 meter for the station boundary. Whatever is the edge of the station, you consider 50 meter surrounding. You do the precondition survey, whatever buildings are falls in that particular zone. Then you do the settlement analysis. You, by means of empirical correlations are there. You have already done the FEM analysis, where you already model the cut and cover and NATM together. So you can use that settlement trough to get the stage 1 assessment. So simply the buildings which are beyond the 10 mm contour, you have to exclude for the further assessment. Those buildings need not to further analyze. Whereas in the buildings which are within the 10 mm contour are further analyzed for the stage 2 assessment. How you do the stage 2 assessment? I'll be explaining in the next slide. You have to gather the information of the building position. What is the building position with reference to the station, or if you are doing it for the TBM, from the center line of the alignment. So these are the some category. I'll be talking about majorly station. So it is from the edge of the station. What is the distance of the nearest face and the farthest face? What is the height of the building? Whether building is a masonry building, so you consider E by G ratio separately, 2.6 normally. If it's a frame structure, you consider 12.5 E by G ratio. So after doing the detailed stage 2 assessment with individual building which are falling within 10 mm, you see how many buildings are still in the category of B2 or less. Then these buildings are need not to be further classified. Whereas after stage 2 assessment, if these buildings are more than B3, suppose moderate or severe or very severe, then there are 2 options. Whether you do the structural survey of these building, you refine your stage 2 assessment with the help of the inputs which you receive from the structural survey, and then you rule out the buildings which are not further required to be analyzed. But there is another way also, that the buildings which are in moderate or severe category, you do if the structural survey is not at all possible, you can develop a separate protection scheme for those particular buildings. And these buildings are rigorously monitored. It has to be completely repaired in terms of propping. You have to do the crack repair, major repair, wherever it is required, as per the requirements. So that you have to do. So this is one of the example how we do the stage 2 assessment. I explained in the previous slide. You find out the settlement curve from what is your settlement trough with the help of your stage 1 assessment. For example, you have the boundary of the, suppose this is the boundary of the cut and cover station, and then you develop the vertical settlement, and based on the position of the building, what is the nearest face and the farthest face, you find out what is the differential settlement. And based on the differential settlement, you find out the tensile the strain, and accordingly you classify building. One thing it is important, whatever you done the precondition survey based on the influence zone, you can take impact of that precondition survey to your stage 2 assessment to give a combined stage 2 assessment, and then you can classify your buildings accordingly. So one of the project I was trying to explain, we did the similar thing for all the number of buildings lying above these NATM tunnel. You can see clearly the red and orange color buildings are the very conservative buildings where the extensive repair or propping is required. You can see 50% buildings are in the damage category, with the severe category. So these building needs extensive propping and repair. And some buildings where you need a structural survey if possible. If not, you need a detailed protection plan. You need sometime real-time monitoring during the excavation of the station, so that you protect these buildings. because uncertainty can never happen, can anytime happen. So you have to be ready with all sort of uncertainties. Next slide. So one of the example how we give the AAA limits for the buildings. You can see the building settlement points which we provide for different category of buildings have been given alert, alarm, and action level based on the analysis result. We apply the tilt meter on the building walls. So accordingly, we give the horizontal gradient of those particular buildings. We define the floor. What are the number of floors? What are the structure type? Whether it's a masonry building or the framed type of structure. What are the height of the building? Whatever is the existing condition, we also highlight in our detailing. PPV limit, what are the vibration limits allowable? Normally for the critical buildings, we try to keep it 5 mm per second. For fair condition buildings, we try to keep it 12 mm, where in the good condition buildings, we try to keep it 25 mm. And the frequency of monitoring depending on the construction progress. If the excavation is at the early stage, you can monitor it weekly, but during the construction, you have to monitor it daily. It is very important thing. And accordingly, some buildings, it is very important that you cannot exclude all the buildings which are, suppose 10 mm, the buildings which are beyond 10 mm. I understand these buildings are not very critical, but anyhow, we monitor those buildings as well. So these AAA limits are provided for the buildings which are far away, but these are important aspect because the excavation is not far from them. So these buildings also to be monitored. So one of example, you can see I presented a section where the cut and cover station is happened, and then TBM has been passed and NATM has been constructed. So the surface instrument, we provided AAA limit thoroughly at every stage. You can see when the cut and cover taken place 2.8 meter, then 8.8 meter till concourse level, and then till the bottom intermediate level and the base level. And during the TBM also, what are the impact? So we separately given all the detailing. And once the NATM is completed, the separate surface settlement target limits, inclinometer limits, 3D targets, which are falls on the cut and cover walls. There are 4 levels of instrument we recommended. So each one of them we have presented separately for various stages of excavation. Extensometer also we provided, and we try and give the monitoring frequency in form of during the excavation and prior to the excavation and during after the completion of the excavation. Water is of course important aspect. At this particular project, we had a water level of 3 meters, so we were not allowed to draw down more than 2 meters. So 55 meter was kept in the design for doing the analysis, and we were monitoring it thoroughly for this particular project. So as I explained in the previous slide, if you cannot refine your stage 2 assessment with the help of structural survey, you have to rigorously check the buildings wherever is the repairing required, wherever propping is required, wherever cracks are required. You have to show it with the help of the survey, whatever is available from the protection the monitoring reports, which the precondition survey report, and then detailed instrument of these buildings are to be provided. Sometimes regular monitoring with the help of real-time monitoring instrument is also required, which are buildings close to the stations. So one of the example where how we do the propping, you can see the props are being placed for the 2-story building at 1.5 meter spacing, and some arrangement has been shown how we do the propping, and the spacing can be reduced as the height of the building increase. Suppose G+3, you can reduce to 1.2 or 1 meter, and these are the typical detailing for the propping. For the crack repair, there are 2 sort of crack repair. If the cracks are less than 5 mm wide, you take out the plaster, you repair the crack, you fill the sealant, seal the crack, and then you redo the plastering. That is that normally we recommend for the damaged buildings. Similarly, for the buildings which are having the crack more than 5 meter, there is some detailed methodology where you fill the cracks with this. You sealed it completely. You remove the plaster both the side to 50 mm, and then you place the wire mesh both the side, and then you redo the plastering after doing the wire mesh. Some of the buildings which are close to the vicinity of the station, somewhere the building condition is very poor. Some grouting was recommended to enhance the the condition of the top soil layer, because I explained in the previous slide, soil layer is 5 to 7 meter below the ground. So this particular area was grouted to increase the shear strength parameter below the ground. And during this grouting process, very important that you monitor the buildings. Suppose the grouting pressure has to be very much controlled. It should not be like uncertain. You have to be controlled thoroughly, and then you apply the grouting to increase the strength of the ground mass. Thank you so much. I hope it is interesting. Not, I completed within 30 minutes. No, 1 hour, I think. Yeah. If any questions, please. Thank you very much.
Yes, sir. Yes, sir. We will move ahead for the question and answer session.
Yes, please.
So you may see the questions in the chat box. I think we have one question. Sir, this one is the best presentation. It's a good compliment, sir. Question: how to find the medium between DPR stage, GTBT, and the design stage GTBT?
How to find out between the DPR stage, GTBT, and design stage GTBT. So basically, it is definitely when you are the detail stage, you have more number of boreholes, you have more number of monitoring data, so you have extensive monitoring and extensive investigation. So you always refine your results at the advanced stage. So definitely you have a detailed design stage. It is more number of data available with you. So comparative to the DPR stage, detailed design stage, you will be refining your data always.
Okay, I think Rishi here wants to ask something.
Yeah, please, Rishi. Yeah, please.
Yeah. Hi, good evening, sir.
Yeah,
Rishi
good
here.
evening. Yeah.
It was really a good presentation. And to be honest, what Niranjan said, it was one of the very informative presentation. So I have two questions for you. Not questions, to be honest, just one AAA limit which you had set for the tunnels. So can you just go back to it and explain it a bit when this determining the AAA level for the tunnels?
Yeah, I will be going back. And I wanted to thank my team member also. There are Arpit is there and Mayank is there who supported me, and they are also free to answer if anything. However, I'll try to explain. Are you talking about this particular slide for AAA
Yes,
limits?
yes, yes, sir.
So basically for the stress condition, which is stress on the liner, spread concrete lining, we basically get the forces from the RS2 model. You can see this particular. Let me put my pointer on.
Yeah, sir,
You
it's
can see this,
visible.
but yeah. So you can see this 1375 is extracted from the maximum axial force onto the liner from the RS2 output. Then whatever is the thickness, you divide the thickness and 1 meter width, you get the stress, particularly stress for this particular liner. And using this hoop stress theory, we consider this as a thin cylinder. And the stresses are applied all around the liner. So thin cylinder theory is basically internal pressure and the external pressure. We apply this theory to get the pressure. And with this formula, we get the radial stress using the stress onto the liner from the ground. So this 6875 has been used and multiplied with the thickness of the whatever liner we used. 2.2 200 thickness was there, and what is the radius of the section, the tunnel was 5.2 meter to 25 meter. So if you multiply this 6875 multiply by thickness divided by 5.25, you will get this radial stress. So this radial stress we recommend for the radial pressure cell, which we applied into the liner boundary. And definitely for the modulus of the spread concrete, normally 5000 root FCK we consider. M35 is the grade of the concrete. It comes out to be 29 GPa. We consider conservatively 24 GPa, 80% of its modulus. Normally we normally recommend it conservatively. So with the help of stress upon strain ratio, what we have already stress, then with the help of E, we calculated the strain and we converted strain into the micro strain.
Okay.
Okay, sir. Do we have any other questions from the audience?
Yeah, just one more question from me.
Yeah.
Sir, it
Sure.
is actually is on design. So can I go forward and ask regarding the design part?
Yeah, I
So
can open the design slide.
yeah, the confinement one. So I think in the confinement slide, uh,
This one,
the
this one.
no, the one previous to that,
Oh,
I
okay,
don't.
okay. Convergence confinement.
Yeah,
Convergence confinement.
convergence confinement. Yeah,
Yeah, this one.
yeah. So I just had one question, and this you said that this was in I recall is in granular soil and silty soil, right? The cross
So
passages.
the Rishi top layer is our silty sand, where
Okay,
the top 3.8 meter is the filled up material, whereas below the 7.5 meter is the rock grade 4 quartzitic rock, and the tunnel depth is 13 to 13.5 meters. So it's purely in grade 4 rock, the tunnel
okay,
boundary.
okay.
So
So just one.
because it is in the rock mass, we consider the elastic ground behavior, and therefore we
Okay.
use the Mark Pennant approach.
Okay, because yeah, that's what I was thinking. Because in grade four, you are using this equation, and it was regarding the elastic limit. So in this, you are
Yes,
assuming that the behavior is elastic behavior of the rocks.
yes. We are assuming elastic behavior of the rock.
Okay, okay.
Actually,
But if we have
sir,
checked it.
can I add something? Hello?
Yeah, you can. Yeah, you can add Arpit, please.
Actually, for this urban tunneling, na, the strength of the rock mass are much higher than the in situ stresses. So that's why we can keep it like it is. Behavior will be elastic during
Thank you, thank
excavation.
you, Arvind. Yeah.
Thank you,
And
Arpit. If any more question, you can mention to me, or you can interact with me separately. Also, no problem. You can type it on the chat.
Yes. So I think your presentation was so good that audience may not be having any doubt at the moment.
No, they can
So
ask me anytime. No problem. I can
yeah, it
answer to
definitely was, to be honest.
separate.
It was quite informative and quite in detail. So we are very grateful to have you, sir.
No, thank you
it
very
it
much. And there are people involved, including my colleagues Arpit and Mayank and Manjeet. So there are many colleagues in my company. Seniors are also supporting us, so we can able to deliver more number of presentation. Similarly, because we deals in range of problems, and we will happy to share our knowledge with the other members, and also to gain from people who are belongs to the same industry. So it will be helpful to share the knowledge.
definitely,
Mm.
sir.
Yes,
Yeah.
sir.
Definitely,
And
sir.
Geoconsult has been a long partner with TAIym as well since beginning. It has given us a lot of support. So thank you, Geoconsult and the team for that.
You are welcome. You are welcome.
Yes.
Always welcome.
Once again, I would like to conclude this webinar by saying thank you very much, Mr. Jitendra Manwani, sir, for a wonderful webinar on urban tunneling interaction and challenges. I am sure that your experience will be very useful for everyone and hope our student members have got a clear idea about today's topic. I would like to inform that our past webinars are also available on our YouTube channel, and this webinar will be uploaded very shortly. Before signing off, I would like to request you to renew everyone to renew their membership for the TAIym. I would also like to invite new members to be part of the TAIym, which is solely focused on bridging the experience of professional working in different projects and also act as a platform to share technical expertise in the field of underground construction. And there's always many additional benefit of being a member. So grab a chance of being one. Once again, thank you, Mr. Jitendra Manwani, sir, for sharing your experience. Thank you all for joining. Have a great holidays and Merry Christmas in advance.
Merry Christmas and Happy
Thank
New
you,
Year in
Aditya.
advance.
Thank you, Rishi. Merry Christmas to
Merry
all.
Christmas,
Thank you.
everybody.
Yes. Thank you, sir.
Thank you.
Yeah, thanks.